This is 5-1 inverse functions. The first type of example that we'll look at is finding the inverse of just a bunch of ordered pairs. So if I give you, for example, negative 8, 5, comma 4, negative 2, negative 7, 1, and 3.8, 6.2. Okay, and we have this in set notation. There's some little set brackets around each side of it. If I asked you to find the inverse of this, all I do is switch the x values with the y values. So my inverse of h will be equal to 5, negative 8. I don't switch the signs or anything. They keep their own signs. Negative 2, 4, 1, negative 7, 6.2, and 3.8. That's the end of the set, so I try to close off with a set bracket. Okay. So if I had, for example, just some of these plotted on here, what's actually going to happen with these is that it's basically just going to get flipped across this line here that I just drew, which will be the line y equals x, is the line that everything's going to get flipped across. So I can't graph negative 8, 5, but 4, negative 2 is now going to go to negative 2, 4. And if I really notice, this is, if I drew a line here, it would make a 90 degrees with it. Not that that really matters. I'm not really worried about that. All that we're just doing is just graphing the inverse if it asks you to graph them, which most of the ones with points are not going to ask you to graph them. Okay, but everything gets flip-flopped across this. And just like how we made our inverses of the points by switching the x's and y's, we can do the inverse of a function if we were given y equals x squared minus 5x. We're going to switch our x's and y's out in order to find our inverse. So then the inverse, in the most basic form, would look like x equals y squared minus 5x. On the questions that ask you to simply find the inverse, all you have to do is actually replace the x's and y's. And then there's some of them that ask you to regraph it then. Okay, but we really do not know how to graph this. I mean, like, you could just plug in points and do that, and that'd be fine. But what we're actually going to do is solve for y, and I should have made that a y as well. Okay, so in order to graph this, what we're actually going to do is graph our original function. So we have x squared minus 5x. Okay, so what I'm going to do is I'm going to solve for my zeros in order to know where to plot this, really. I know that since I really don't have anything out here, good, it's going to go through 0, 0. So I have x squared, and that would leave me with x minus 5. So I would have a 0 at 0 and 1 at positive 5. So that's one of my zeros, and then I'm going to go out 1, 2, 3, 4, 5. And since I know it's a positive graph, it will look something like this. Okay, and then what I'm going to do is I'm going to go on, and in order to graph this thing, I'm going to flip it across this dotted line that I have here. So what I'm going to do is actually I'm just going to grab this. I'm going to redraw a graph on here. And then I'm going to grab this. And any points that I had in common on the actual line here will still be there. So this still needs to go through 0, 0 because it was actually on the dotted line. And then if I look at it, it should also go through positive 5 on the y-axis. 1, 2, 3, 4, 5. Okay, so those are easy reference points or along your x and your y-axis to make sure that they go through those points still. And this is honestly what my graph would look like for a lot of your problems. So if I had been given just some graphs, so a table, a function table of values, if the year previously was my domain, it doesn't really matter what it is here, if it's a year, what it is, and my range, they said, was postage. Okay, the cost of postage. In 96 and in 98, the cost was the same amount, and it was $32. And then in 2000, it was 33 cents. I think I just said dollars, but it's cents. In both 2002 and 2004, the cost was 37 cents. Okay, so all that happens when we find the inverse of this is the domain and the range will get switched. If you want to make a new one, I'll make a new one too. Now, my range will be my new domain, and I will leave everything just in the same places. My domain now is over here, and my range is now the year. So this is what actually happens when we take the inverse of something, is that basically just all our numbers, the arrows go to different directions. It means that 32 will point to two different things. It will go to 96 and 98. 33 cents still only goes to 2000, and 37 cents goes to 2002 and 2004. Okay, if we were to look at this, this would not make a function. Okay, and that's fine. Our inverses are not necessarily always functions. When we are finding functions, if, for example, if this was our f of x, what we're going to do is call this our f inverse of x. So that will always be how this is read, is f inverse of x. And we'll start using that a lot. Okay, sometimes we're given a function, but the inverse of the function is not actually a function. Whoops, I want is not actually a function. In order to see if it will be a function before we ever try to graph it or do anything else with it, what we're actually going to do is a proof to show that it's not. So we'll do a couple of these because sometimes they get really weird. But what I'm going to do is if I'm given the function, so I'm given the function f of x equals 2x minus 3. And just this is a linear function. Most linear functions will work. So when you have to prove it, you should pretty well be able to recognize that this will work or will not work. Okay, so what I'm going to do is I'm going to say that I want to show, so this means want to show. And you guys have probably done proofs in geometry. This is more of what an algebraic type of proof would be. And this is not by any means like a full proof, but this is what you do later on in some higher level algebras in college. So I have this function, and I want to show that a equals b. And we're going to do a proof by contradiction. I can't spell contradiction. There we go, maybe. So in order to do a proof by contradiction, we say basically what we want to prove at the very end, and then we come back and we say the opposite of what it is that we want to start with. So then what I'm going to do is I'm going to plug in, or at first I'm going to say A is not equal to B. That's the first step. And you'll basically go through the same steps every time. I'm going to plug A and B into my function. So then I'll have f of A equals f of B. I'm going to set them equal to each other, and hopefully I will always get A equals B at the very end. Okay, f of A, I'm going to plug A in. I have 2A minus 3 equals 2B minus 3 when I plug in B on this side. I'm going to add 3. I need to solve these things. Plus 3, but those both add to 0, so then I have 2A equals 2B. If I were solving for one of these variables, I would divide by 2. That will multiply to 1. And then I get A equals B. This was a contradiction from what I just said. And so what I would write then to show that it's a contradiction is 2 arrows pointing towards each other, which in math means contradiction. And therefore, so I'm showing you a lot of little symbols. So therefore, instead of writing therefore, what you're going to write is 3 little dots that make a little triangle. Therefore, A equals B, and the function is 1 to 1. Another way to write 1 to 1 that I would usually write is just 1 dash 1. It kind of looks like an H. Try to keep it from looking like an H. Or you can actually write like 1 to 1. That might make it a little bit easier to read. But sometimes it's easier to actually understand 1 to 1 because this is a very weird, algebraic proofs are very weird for a lot of people. What we're actually going to do is I'm going to show you an example of something that's not 1 to 1 and how we can find it easily without doing a proof. However, some of the homework does ask you to do a proof. And the previous steps that we just did would be a proof. Oops, I didn't want that one. So what I'm going to do is if I have a parabola, I'll do what we just graphed. We just graphed a straight line, and this would look like we had 2x minus 3, so minus 1, 2, 3, and we go up 2 over 1 every time. So this is what my graph would look like. And then I have a test, which is called a horizontal line test to test if something is 1 to 1. So 1 to 1 test is a horizontal line test. And just a reminder what our to test if something is a function. So our function test would be our vertical line test. So what happens is I could have then my vertical line test. So this is indeed a function because it only passes through one time. So let's try to erase some stuff because we don't need it all on there all the time. So what we have is a function that is 1 to 1. So if you guys want to graph your function first in order to kind of actually see if you're going to get A equals B at the end in your proof, you can do that as well. But if you're good with doing the proof, it can be easier to just get the proof done and actually do it. Okay. So this is an example of something that is one-to-one. So now we're going to prove that we're given g of x squared. G of x equals x squared. We want to prove that basically g of x is not one-to-one. What we're going to do is we're going to go through the same exact steps to either show that it is one-to-one. So I want to basically say at the end that A is not equal to B. The easiest way to show that something is not one-to-one is usually to give an example. X squareds are fairly simple to do this with, because even if I were to go through my proof steps, a lot of the times you guys won't notice that there's actually two answers to an x squared, and you will most of the time think that you've proved that it is one-to-one, even though it was a proof that it wasn't. So I need to pick two numbers to prove that it's not. What we're going to do is pick two numbers that are different, that we think will give us the same output. So it's fairly simple. If I pick something that has a perfect square, if I plug in, let's say, -4 and 4. What we're going to say is -4 is not equal to 4, so let's plug those both in. G of -4, and I want to show that that's not equal, or that is equal to G of 4. Then I plug in -4 squared equals 4 squared. And I want to see if this will work or not, and I have 16 equals 16. I have the same thing. And usually when we actually go back and go through these proofs, what we're doing is basically working from this step and going backwards to say that these numbers have to be the same. But anytime I have an x squared function, I can usually find something that will not work. So if I scroll back up and I actually graph this function on this same one, or I will just make a new graph, how about that? And my graph of x squared, you guys should be fairly familiar with, so I'll just go ahead and draw it. It will go through at 0, 0. And I have a parabola. Sorry, my pen is being a little fuzzy. Okay, this parabola, what this means is at -4, 1, 2, 3, 4, I'm going to have 16 on my graph, but also the same thing will happen at +4. I will get 16. Those give me the same function value. This is where I will be doing the horizontal line test to test if it's one-to-one. And the horizontal line test works the same way as the vertical line test because this crossed at two places. Every time it doesn't have to be every time that it'll cross at two places. But as long as it crosses one time in two places, this is not one-to-one. And I'll spell it out. This is not one-to-one. So if some of the problems ask you to determine whether something is one-to-one, you can just use your vertical line test, do a quick graph, or your horizontal line test, I'm sorry, and do that real fast, and that'll work. If it asks you to prove it, though, you need to go through these algebraic steps and find a counterexample if it says prove that it is not. And to prove that it is, say A is not equal to B, but I'm going to plug them in anyway, and I'm going to get the same thing at the end. And then what you're going to have to do is you're going to be given a few problems where you'll actually have to go through and they will give you a function and you'll have to find the inverse. So if I give you the function f of x equals 2x minus 3, can make that a little bit bigger, sorry. I ask you to find the inverse. So find f inverse of x. So what I'm going to do is I'm going to go through and I'm going to change this to a y equal. So y equals 2x minus 3. Then I switch my x's and y's. Switch x and y's. So then I have x equals 2y minus 3. And then I need to go back in and solve for y. Okay, some of the questions don't ask you to do this, but some of them do. So I'm going to add 3 to both sides, and I get x plus 3 equals 2y. Then I divide by 2, and I divide everything by 2. I'm going to write my y on the left side, since that's what I'm really used to, and I get x plus 3 over 2. That's how I find f inverse of x. I replace the y with the f negative 1 of x, so f inverse of x equals x plus 3 over 2. So that's the steps you'll have to do. The linear ones are usually pretty nice, so let's do one with a cubic function. So I give you g of x equals x cubed plus 2, and I want you to find g inverse of x. So I have y equals x cubed plus 2, and then I subtract 2, or I replace my x's and my y's, so I have x equals y cubed plus 2, subtract 2, subtract 2, x minus 2 equals y cubed. The way that we get rid of a cubed root, or a cube, is to cube root it, and I will be left with y equals the cubed root of x minus 2. And then I will also ask you to test whether or not something are inverses of each other. So if I had this original function, or this inverse that I just found, we want to make sure that it is actually an inverse. So I gave you this, and we had our original inverse, or our original function of this guy. I want you to check if these two numbers will be inverses of each other. The way we check to see if something are inverses of each other, if f and the given f inverse are actually inverses, is we compose them with each other. Remember, we had our fog and goff. Now we'll do f of f inverse of x, or we can also do f inverse of f of x. And we actually do need to do them both because we need to get our output needs to be x whenever we do this. So we need to test them. So we'll do one that we found ourselves, and we'll hope that it works. So what I'm going to do is I'm going to put f inverse inside of my original function. So what that's going to look like is I'll have f of x plus 3 over 2. So what that's really going to mean is I start out writing my f function. Instead of x, I write x plus 3 over 2 minus 3. So instead of x, I wrote this. Okay, and then I just do some order of operations to simplify it. 2 times this whole thing divided by 2, those 2's will multiply to 1, and I will have x plus 3 minus 3. Well, those also add to 0, and I get x as my output. So that is what I want. I get x. Whenever I get x, it's an inverse. But I need to also test it the other way. So I'll do f inverse of f of x. So I will start out writing my f inverse And I will write my 3 and my 2. Instead of x, I'm going to write 2x minus 3. So what I'm actually going to do is I'm going to basically take away my parentheses since there's nothing happening out front that I need to multiply through. My 3's will add to 0, and I will be left with 2x over 2. Those will multiply to 1, or divide to 1, and I am left with x. Since I got x both times, they are inverses. So because I got x both times. Let's also do it back on our other function that we did, and I should have actually gone through and wrote f inverse of x is equal to the cubed root of x minus 2. So then I'm going to copy and paste this over to my next page. So actually I shouldn't have named it f inverse of x, I should have named it g inverse of x. And I want to check to make sure that these guys are inverses. So g of g inverse of x will look like x cubed instead of x cubed plus 2. I'm going to write the cubed root of x minus 2. Well, what happens is the cubed root and the cubed cancel each other out, and I'm left with x minus 2 plus 2. Those add to 0, and I will be left with x. So g of g inverse of x equals x, so good, that piece is good. Then I'm going to do it the other way around, so I have g inverse of g of x, and I want to get x out as well, so I'm going to start writing g inverse. So this had a big old cubed root. Instead of x, I'm writing my original function, which was x cubed plus 2. I'm going to go through and I'm just going to go ahead and add these 2's together. They add to 0, and I'm left with the cubed root of x cubed, which is also x. So this works out good. So since g inverse of g of x also equals x, they are inverses. So we have homework on page 396. I want you to do numbers 1 through 15 odds, or actually I'm going to change that, sorry. 3 through 15 by 3's, 17 through 24, all of them. And then we'll start back at 27 through 96 by 3's again.